Hi everyone. Today I want to solve this FE exam heat transfer problem for you. We're going to make sure we really focus in on those fundamentals. This problem in particular is related to transient processes. That's subsection D here under the subject heat transfer from the FE mechanical specification. We're also going to touch on a calculator topic today, which is on linear interpolation, and I'm going to show you guys how to do that on a calculator like the TI-36X Pro. The first thing I like to do is read through the problem slowly and just see exactly what they're asking me for. So we're going to do that first. A solid aluminum sphere is pretty much hot initially, and it's exposed to convection. And as it's exposed to convection, we're looking for the time that it's going to reach a certain temperature. So we have a sphere. It's hot. It's dropped into a cooler fluid, and it reaches 150 degrees C. We're looking for a time that it's going to reach a certain temperature. By the way, you can try this problem for yourself using the first link in the description below. Let's go ahead and compile some of these inputs. So we have a radius equal to 0.05 meters, given as 5 centimeters above, a thermal diffusivity and alpha value equal to 8.4 times 10 to the minus 5 meters squared per second, a thermal conductivity K equal to 12 watts per meter Kelvin. By the way, alpha is just a combination of some heat transfer properties. So that's the thermal diffusivity alpha. It says that this object, the sphere, is initially at a temperature equal to 350 degrees Celsius. And it's exposed to a fluid with a convection coefficient of 100 watts per meter squared Kelvin. We have a fluid temperature, T infinity, equal to 50 degrees Celsius. And the center temperature is going to reach in the end after a certain amount of time, 150 degrees Celsius. We're asked how much time is that going to take to happen? Okay, so the first thing that we have is if we have a kind of transient process in heat transfer, we really have two options where we can either use a numerical solution, which we use if we can't use the first option, which is lumped capacitance. Lumped capacitance, if we go into the official FE reference manual here, version 10.4, we go to page 206 approximately. What we see is that lumped capacitance is essentially a model that says that the temperature anywhere in the body is exactly the same, but the temperature is changing with time. So at a time like t equal to 10, the center and the outside surface, they'll be at pretty much the same temperature. And how we can know if we can use this simplified model is if the Biot number, which is a dimensionless quantity, if that's less than 0.1, and we can calculate the Biot number. So that's the first step in seeing if you can use this simplified model, lumped capacitance. If we can use this model, then all we need to know is some things about the starting and initial temperature of the body, and then this T infinity value is for the fluid. What's the fluid temperature? We can compute this beta value, which is some properties of whatever kind of heat transfer that's going on. It's a property of, we can compute this beta value, which is a property of whatever kind of heat transfer values that we have. And once we have that beta value, we can compute the time to reach a certain temperature. So that's our plan. Let's first check to see if the Biot number is less than 0.1. So that's our first step. The Biot number is equal to H over K, the ratio of the volume to the surface area. Now note for a sphere, if we have H over K, the volume of a sphere is 4/3 pi r cubed, and the surface area of a sphere is 4 times pi r squared. You can see this ratio kind of simplifies to radius over 3 here. Okay, if we plug in some of our values, what we get is that the Biot number is equal to H, which was 100, given right here, 100 watts per meter squared Kelvin, divided by our K, which was also given, that's 12. The radius in meters is 0.05 divided by 3. What this ends up being is, we have a calculator right here, 100 divided by 12. That is equal to this value, multiplied by 105 over 3. Okay, 0.139 pretty much. Now that's our BO number, and you can see that it is greater than 0.1. So that means that lump capacitance is not applicable for us. We have to see if we can try something else. And that something else is the kind of numerical solution that I was hinting at before. You can see that if you scroll down one page here, it says approximate solutions for solids with sudden convection. And what we're seeing here is that we have a few different shapes, a few different options, and the form of the equation is pretty similar. The only thing now is that we have to find these constants C1 and zeta 1, as well as there's a Fourier number. That's a dimensionless term in here as well. But it's a similar form to the lump capacitance, but we have to check some tables here. So we have the case of a sphere, and if you scroll down here to the tables, we check out for a sphere, there are some zetas and C1s, and we need to first compute our BO star value. Note that the BO star is not equal to what we had for the BO number. The BO number that we had was HR over 3K. This one is HR over K, right? So what we essentially do is triple our actual BO number that we just computed, and we get a value of 0.4167 here, basically. Let's go ahead and write that down. BO star is equal to 0.4167. And if we check inside the table for a BO number like that, a corresponding zeta and C1, you can see that it will be somewhere between this 0.4 and 0.5 value. So what I'm going to show you right now is how we can calculate that zeta and C1 using linear interpolation from the calculator. If we go ahead and plug in our tabular data here as, now how you get to that is you can just click this data button right here. You can see that what I inputted here was BO stars, my X value, the L1 list, and then I have two separate Y values. The first one is zeta here. You can see 1.05 and 1.16 are my first two zeta values. And then I have C values as well, 1.11 and 1.14. Let's talk through exactly why I'm doing this and how this works. What I'm saying here is that I have a coordinate plane with BO star on the x-axis and either a zeta or a C on the y-axis. And between my bounds, which I know BO star, 0.4 and 0.5, there is my point of interest, which is 0.4167. Now, what I want to do is for that 0.4 and 0.5, I know there's, let's say, zeta value associated with those 2 points. I can create the equation of a line, y equal to mx plus b. And what I can do is plug in for x my 0.4167 if I knew the equation of the line, and I can output a zeta value, right? So I know what this value is. I can get a zeta 1 value or a C1 value if I can make that equation of a line, which I can using the data that I just inputted. So I'm going to show you guys how to do that. First thing we're going to do is click second, and then this stat button here. We're going to scroll down to the linear regression option, which is option 4 here, and click enter. We're going to create a equation of a line for x equal to BO star and y equal to zeta. That's L1 and L2 here. Once we go ahead and calculate this, we get a constant a and b that represents the slope and the y-intercept. We can go ahead and quit out of here and note that you can access the slope and the y-intercept from these variables here in the calculator. A was the slope. We could take that slope and multiply it by our input value, 0.4167, and we can add the y-intercept. And we get a value for zeta 1 at that 0.4167 value equal to 1.0716. And what about our C value? We can repeat the same process. We have to recompute our equation of a line, so we follow back those processes. Except now we're going to use L1 and L3. Go ahead and perform that calculation again. We get a slope and a y-intercept, which is stored in the calculator. We can access it from this button here. A times 0.4167 plus B. Ooh, okay. Okay, so we get a C value here of 1.121. Great, so now we have zeta and C. Before we solve the rest of the problem, if you're enjoying this video and you're learning something, consider leaving a like and subscribing for more content like this. Additionally, if you're prepping for the FE Mechanical exam and looking for a resource that will help you pass, consider checking out my software, FE Interactive. It's the third link in the description below, and it'll give you access to multiple different sections, practice exams, review and improve sections, as well as a tips and tricks section, which helps you use your calculator better and save time on test day. An analytics page, which ties all of the different pages together. You get data for each of those pages, where you can view, for instance, how you did on each exam, as well as a detailed solution manual for each exam, so you know exactly where you're making the mistakes, what exactly is the misunderstanding coming from, and all of those are tied together with an overall data point. The overall data point can be reorganized in terms of performance so that you know what are my top three subjects, what are my bottom three subjects. Having this kind of data is super valuable since it helps you isolate your weaker points and fortify your strong ones. I'm confident that my software, FE Interactive, will help you pass the FE Mechanical exam. And again, you can check it out using the third link in the description below. You get 2 months of access for $10. Let's get right back into the video. And that's pretty much all we needed the calculator for. So I'm going to get rid of this now. And we're going to go ahead to solving the problem again. Now that we have that zeta and C1, we just need to kind of solve this equation here for our time. And the time comes in that Fourier term. The Fourier term is given right up here, alpha t over r naught squared. Let's go ahead and plug into this equation, do some algebra, and then we'll be able to solve. Okay. So right here we have some of these values. We know that the Fourier number, Fourier is alpha t over r naught squared, and we're going to solve for that t term. So the first thing I'm going to do is write down t naught minus t infinity divided by ti minus t infinity. I'm going to go ahead and multiply that by C1. That's this term right here. That's equal to e raised to the negative zeta squared Fourier. I can take the natural log of both sides to get rid of that e term. And then I have a negative zeta squared alpha t over r naught squared. I'm going to go ahead and solve for t. So I'm going to grab some of these inputs up here, which I compiled, and we're just going to plug into this formula. And then we'll have our solution. Okay. The first thing is that, let's go ahead and plug in the time. The negative r naught is 0.05 squared divided by alpha. That was 8.4 times 10 to the minus 5. We have a zeta value that's 1.0716 that we got from interpolating. The natural log of T naught. T naught is, that's the temperature that the sensor is going to be at a certain time. So that's going to be this 150 degrees right here. 150 minus T infinity. T infinity is the fluid temperature. That was at a temperature of 50 degrees. We're going to go ahead and divide by C1. That was 1.121. Multiply by Ti, that's the initial temperature of the body. The initial temperature was 350 degrees for that sphere. And T infinity, we just wrote that down, that was 50. If we go ahead and plug in all the numbers here to our calculator, what we get is a value of around 31.4 seconds. So we're going to check to see which answer is most nearly that answer. 31.4 is pretty close to 32 here. So we can check that answer and view the explanation. If you don't really have time to watch this entire video, what you could do is you can try the problem for yourself. That's the first link in the description below. And you can view these typed or handwritten solutions once you attempt a problem. And yeah, you could save a lot of time like that and get a place to practice for your FE exam. I hope you enjoyed the video. Thank you for watching. Leave a like and subscribe for more content like this. I'll see you in the next video. Goodbye.